your sake, we have changed the time, beta. You should be very prompt with the time, right?
Yes, ma'am.
You were not there when I taught these basic terms. So can you go through it once?
Okay, ma'am.
I'll upload the material in the resource. From there, you download it and please go through it. It's really
Ma'am,
very terms. Yeah,
ma'am, can I say something?
yeah. Why not? Please.
Yeah, ma'am. Ma'am, actually, I'm feeling like we are going a very bit too fast, because of which I'm not able to catch up everything.
Is it?
Yes, ma'am.
Are you feeling that we are going too fast?
Yeah, kind of, ma'am.
Okay. How come, beta? Actually, we have, I think, 5 chapters, and within this 2 months, we're supposed to finish it. And we're not supposed to finish only with the theory. We have to solve number of problems as well. And
So
then,
this is still just the bridge course only?
sorry,
This is still just the bridge course?
yeah, that's what I'm telling you.
Oh, acha, okay, that's why we're doing it. So I thought we have started with
What
the
you, what you
chapters
feel?
now.
What you feel? What is exactly? What was your opinion?
I didn't get you, ma'am.
No, what you thought about it? Like, what you feel like? Is it 12th grade you're thinking about, or a regular 11th you're thinking?
It's
Pretty
the,
sure you thought that it's a regular 11th board, is it?
yeah, exactly, ma'am. That's what I thought.
No, no, no.
So that's why I thought it was a bit too fast for
No,
me.
it's a bridge course because these terms would be again repeated in your grade 11.
Oh,
It's just
okay.
an overview, no, for the just to fill in the gap in between your grade 10 and 11.
Ma'am, as what I know is that probably these bridge course will end in the first week of May, right?
Most probably.
Okay,
So we have to go a little fast. No? We are on third chapter.
understood.
More
Okay, ma'am.
chapters are you
How
getting?
many do we have in total?
Sorry?
How many do we have in total for chemistry?
5 chapters are there, I guess, as per my
This is the
knowledge.
fourth one.
Third one.
Oh, okay, huh?
Got it?
Yes,
And
ma'am.
I'm going slowly. I'm not going too fast with it. If you think like hardly 4 5 terms I teach in one class, not more than.
Okay, ma'am.
So till others are joining, I'll explain you about the previous terms. Okay.
Okay, ma'am.
Fine. So I'll let you know what it is exactly, dipole moment and the resonance. Yesterday you were not there na, when I taught about the resonance and the dipole moment. From bond angle you were not there. Na? Bond length I taught that day you were there.
Yeah. Yes, ma'am.
Right. Here, bond angle. This side see. What do you mean by bond angle? Yeah. It is defined as the angle between the lines representing the orbital containing the bonding electrons. For example, if I would say this is oxygen, this is hydrogen, this is also hydrogen. So these are what?
Good afternoon, ma'am.
Good afternoon. Who's this?
I'm Dhananjay, ma'am.
Dhananjay. Dhananjay, just give me 2 minutes. Let me revise her about this term. She wasn't there that day, okay?
Okay, ma'am. It's fine.
Now, these are what? Orbital bonds, right? And the
Yes,
angle
ma'am.
between these two orbital bond is nothing but what? Bond angle. And it is expressed in terms of degrees. Which terms?
In degrees.
So this is very basic. It help in determining the shape. By looking at this, we can confirm like the shape of water molecule is angular shape, correct? It can be expressed in degrees, and experimentally it can be determined by the spectroscopic method. So what is a spectroscopy? That you will come to know in your masters, even in your
Okay.
graduate study detail in chemistry. Okay?
Okay.
The kind of chemistry where rays has been bombarded onto the molecule to find out the structures. Okay. The next one would be bond enthalpy. What is the bond enthalpy? It is nothing but the strength of bond. Bond enthalpy is nothing but what? Strength of bond. See what is given. It is defined as the amount of energy required to break 1 mole of bond of a particular type of separate them into a gaseous atom. And for example, if you say water molecule, okay, so 1 mole of water molecule bonds, if you want to break, how much energy you would require to convert them into hydrogen and oxygen separately. This is called as the
Okay.
bond enthalpy. Fine. So what they said, greater the bond enthalpy, stronger is the bond. Right? They are given here. Hydrogen bond enthalpy is 435.8 kilojoule per mole. Right?
Yes.
Bond enthalpy is related to the bond multiplicity. Means if bond multiplicity is increases, bond enthalpy is also increases. For example, carbon-carbon single bond has a bond enthalpy. Here they have given 347 kilojoule per mole. Carbon-carbon double bond, when it becomes, so carbon-carbon double bond is stronger as compared to your carbon-carbon single bond. And hence its
Actually,
bond,
more the bond multiplies, the more the bond enthalpy increases.
it is
Okay.
610. Yes, Dhananjay. Yes, Dhananjay, you said something?
No, ma'am. I didn't say anything.
I'm not, I didn't hear you properly. So I'm
No,
asking
ma'am.
you.
I didn't say anything.
Okay, okay, fine, no issues. What about just one? Just one, someday he joined, someday he disappear. What happened, just one? How are you? Just one, am I audible?
Yes, ma'am. Yes.
So one day I could see you for a few minutes, one day you would be left all of a sudden. Why?
Ma'am, actually, I am in village, so there's network issues.
Okay, try to get in a proper network better because the concepts are really very important. Okay, fine.
Ma'am, can I copy it down?
What? You
Yes,
want to
ma'am.
copy down?
Yeah.
You can, or else I'll like, take a screenshot if you want. Better. Don't want to
Oh,
waste
okay.
because you already these terms I have taught to the Dhananjay. Dhananjay was there.
Yeah, 1 minute, ma'am. I'll take the screenshot.
Are you understanding what I tried to say? Because he will miss his class now. Already he learned all those things. Fine. Just want you to do same. Please take a screenshots.
Yes, ma'am.
Shall I erase it?
Yeah, yes, ma'am.
Fine. Now we are going to go to the next part. That will be resonance, I guess. Bond order. Okay, I'll let you know what is the bond order. It's very easy. And the C, bond order means what? According to the Lewis in a covalent bond. Bond order means what? The number of bonds present in between the two atoms. See, the bond order is given by the number of bonds between two atoms in a molecule. For example, if you see the H2 molecule, it has the bond H only single bond in that. So bond order for the hydrogen molecule would be 1. For the oxygen, if you see O2, one oxygen is attached to another oxygen by 2 double bond, and hence the bond order would be 2. Similarly, the nitrogen attached to another nitrogen with 3 bonds. Here it is given 2. So you don't have to think about it. There are the 3 bonds in between nitrogen molecule. And hence its bond order is 3. Okay, here is a printing mistake. Clear?
Yes, ma'am.
What do you mean by bond order? Bond order is the number of bonds present in between the two atoms of a molecule. Right? For example, you can
Yes.
see fluorine 1, oxygen 2, right? And nitrogen has how many? 3. Now, one more thing is given, isoelectronic. See, this is very important. Isoelectronic molecule and ions have identical bond orders, right? For example, F2, O2 minus 2, and both these have a same bond order. For F2, if you see fluorine attached to another fluorine, so there would be bond order 1. But then if you see atomic number of fluorine is 9. This is also 9. So total number of electron 9 plus 9 is equal to 18, correct? Atomic number is equal to number of proton and number of proton is equal to number of electron in an atom, correct? Yes or no?
Yes, ma'am.
That's the number of electron present into F2 molecule is nothing but 18. For the oxygen, O2, it O2 2 minus, right? One oxygen has atomic number 8, another oxygen has atomic number 8, and this 2 minus is nothing but the electron by adding inside it. So that these are the 2 electrons. So total would be 8 and 8 16, 16 and 2 18. You can
Oh,
see fluorine and oxygen are isoelectronic with each other, right?
yes, ma'am.
Yeah. So whenever the species are isoelectronic, bond order would be same. So if fluorine has a 1 bond order, then O2 2 minus also have the bond order 1. Clear?
Okay,
Fine.
ma'am.
This thing you have to keep it in your mind. Fine. Now see the next one.
Ma'am, what will be the structure for the O2 minus 2?
O2 minus 2.
Huh? Oh,
And
okay, understood.
one bond would be there. Wait a minute, I'll let you. Actually, normally we know this, right?
Yeah,
Get shifted over here. Correct?
right, yes, ma'am. Okay, it breaks down and then it becomes
Yes.
minus 2.
Lone pair would be shifted. That pi bond has been shifted as a lone pair on one of the oxygen.
Okay, right,
Clear?
ma'am. Yes.
Now see the next one. Now this is about the ozone. Ozone structure is given to you. Fine. You can check in oxygen here. One bond is there, so bond order is 1. Here means like this second and third oxygen, if you check, there would be 2 double bond is there in between second and third oxygen, and hence the bond order in between these is 2. Same nitrogen, right? First
If
oxygen.
there, ma'am, so if there are more than two types of bonds, like if it also has one bond and double bond, so the highest number will be the bond order.
No, it won't be. Bond order would be is not. It won't. It's an individual bond. It's related to the individual bond. It
Oh,
won't
okay.
be complete molecule. Okay. Bond order is related to that particular bond only. It's not related to your
So
complete.
between NO, it is
In
between
between two
first NO, it is only 2.
yes. You can
Okay,
see nitrogen and this first oxygen has only one bond. So bond order in between this nitrogen and oxygen is 1. You can
understood.
see about this nitrogen and this oxygen, there are the 2 bonds and hence the bond order is 2. And here is only 1. Clear?
Okay,
And hence you have to keep it in your mind what bond order is related to only number of
one.
atoms. It's not related
Okay,
to molecule in between 2 atoms. Clear?
okay, ma'am. Between two atoms in
This is
one
the resonance
molecule.
structure and it is quite important. Already I taught this, but then yes, both of you, Jaswant and what his name? You, Shreyasi, right? Sorry.
Ah,
You were not there and hence I need to repeat it again. Dhananjay already learned it. He was present. Okay. See about the resonance structure. There are many molecules whose behavior cannot be explained by the single Lewis structure, Lewis acid structure actually only Lewis structure is not. It is extra over here. Okay, Lewis structure. And the examples are given. Lewis structure of ozone represented as follows. For example, oxygen over here, right? It's a single bond, another oxygen, and here it is a double bond. Clear? This is your ozone structure. So what you come to know over here, it would be with negative charge, right? Yes. And here is a delocalization of,
yeah.
right? It's a lone pair. Here is a negative charge, and here won't be the lone pair. Fine, no issues. Clear? Understanding up to this?
Yes, ma'am.
I have given here dots, and that is none of our concern currently. But then these negative charge can be delocalized. It will be shifted over here, and when it will be shifted here, what happened? This double bond will be goes and shifted on this oxygen.
Oh,
I think this is your first oxygen, second oxygen, and third oxygen. So what happened in short? Whenever you show the canonical structure, you're supposed to show it with a double-headed arrow. Keep it in your mind. Fine. How are you supposed to show? With a double-headed arrow.
hmm.
This oxygen and first oxygen and second oxygen would be formed double bond, right? And second oxygen and third oxygen would be formed single bond, and the minus charge would be delocalized onto the third carbon. Means in short, your negative charge has been shifted from first carbon to third carbon. Clear?
Yes, ma'am. But why are we doing these, ma'am?
Yeah, that's what I'm telling you. Why
Okay.
this happens? Because there is a delocalization in between this bond. They are the alternate bonds. Here is a negative charge, right? Extra electrons. Here is what? Single bond, and here is a double bond. Means double, single, double, we can say. This is double, single, double. Alternate bonds are there. Whenever alternate bonds are there, these atoms are used to give us a resonating structure, which is called as the canonical form. What does it call?
Canonical form.
Means we cannot predict them where exactly this negative charge is present, whether it is on first oxygen or whether it is on third oxygen, right? So it is means like not confirmed where exactly it is present, and hence we can't say like from which suppose oxygen this ozone molecule is been attacked or would be react with some of the another molecule. It will be react with your first oxygen or with your third oxygen. We can't say. Understand? And because
Yes.
of you have to consider both the structures. You have to consider both the structures. And these structures are called as what? Resonating structure. What does
Okay.
it call?
Resonating structure.
Structures. And the phenomenon is called as resonance. Phenomenon is called as what? Resonance. Fine. And you can see a single bond has been converted into double bond, and double bond is converted into single bond. Clear?
Yes, ma'am.
So we can't predict where would be the single bond present and where is the double bond present. And hence, while writing, we have to write these structures in its hybrid form. In which form? Hybrid form. How are you going to write the hybrid form? That I'll let you know. In this way. It's generally oxygen, oxygen, and oxygen. This is your ozone molecule. Okay. So here would be a dotted line you have to show. Here also a dotted line you have to show. And this dotted line will be represent either double bond or single bond. This dotted line may be
It
present.
shows the possibility whether it can be on this side or this side.
Sorry.
It shows the possibility whether double bond can be on
Possibility.
either
It may
side.
present, it may not present like that.
Okay. Hmm.
Okay. And this structure is called as what? Hybrid structure. This is called as what? Hybrid structure.
Or it can be resonance hybrid also.
Yes. These forms, first and second is called as what? Canonical form. And third is called as what? Hybrid structure. Clear? Fine. Now we'll move down. Same things can be shown by the many of the compound. You might have heard about the electron donating effect and electron withdrawing effect of the groups present onto the benzene last year. Inductive effects, resonance effect. Have you learned about it?
No, no, ma'am, we haven't.
Just one? Are you aware about it?
No, ma'am.
No. Fine. So wait a minute. So this is what? Phenol. This structure is of what? Phenol structure, correct? This is your
Yes.
benzene. Double, single, double. Here is the OH group. So this OH group on the oxygen, there is a lone pair, correct? Right? So this lone pair can be delocalized in this ring. Okay, can be delocalized in this ring. How? This oxygen will form a double bond in between your oxygen and first carbon of benzene. This is your first carbon, second carbon, third carbon, fourth carbon, fifth carbon, and sixth carbon. For your more understanding, I'm explaining, okay, in this manner. Fine. And when it will become, your internal double bond has been shifted onto the second carbon, right? And vice versa, things would be happen in that manner. I'll let you know how. But then what you know, OH group has a lone pair. It shifted its electron in between oxygen and carbon. And these electron, one pi bond has been formed by how many electrons? 2 electrons.
2 electrons.
We generate a negative charge. And that negative charge would be rotate onto the ortho, para, and again ortho position. One by one. I'll let you know how, and your canonical structures also I'll explain you. Right. So these delocalization of negative charge also we cannot predict where it is, whether it is at ortho position, whether it is at para position, whether it is at again this ortho position, sixth carbon ortho position. Right. And these are the canonical forms you have to frame for the phenol. And same different situation would be occur when electron withdrawing group would be present onto the benzene, because we know that benzene itself is a electron rich. When
Yes.
it would be there, it is also electron rich. That time which charge delocalized, negative charge has been delocalized. But then when there would be the electron withdrawing group, like nitrogen group, like nitrile group, N double bond O, correct? Here it will be O, right? In that case,
Yes.
this is your benzene group, correct? Permanent double bond. Now this nitrogen, though it has a double bond, though it has a lone pair, it is a electron withdrawing group. How it is? It is the electron withdrawing group. This will be the negative charge over here. Nitrite group you might have heard about, and even you have seen there should be the minus charge on it. Clear? What
Yes.
happened? It withdraw the electron from benzene, and this double bond has been delocalized onto the oxygen. Clear? You can check. See. Right?
Yes, ma'am.
What happened when this electron has been withdrawn? It generates positive charge onto the ortho, then para, and again onto the ortho position respectively. One by one. Clear? And that will be your canonical structures. Right? Because what
So
happened?
there are several canonical structure for any single structure,
Yes, yes. There are
level
several
structure.
structure for one molecule, and hence we
Okay.
write a hybrid.
Okay.
We're supposed to write your resonance hybrid. You have to consider a resonance hybrid while reacting that molecule with some of the other reagent or the reactant. Clear?
Yes, ma'am.
Fine. So this is very, very important that you need to keep it in your mind. I'll let you know the structure for phenol and even for the nitrate group one by one. Shall I erase it?
Okay, ma'am.
Fine. I'm going to share with you a whiteboard. There I'll explain you thoroughly. I hope whiteboard is visible to all four of you. Sorry, all three of you.
Yeah, it is, ma'am.
Okay. Yeah. Now here I'm going to draw the phenol structure. Double, single, double. It's a benzene, okay? And it's a OH group with lone pair on it. So this lone pair has been shifted into the oxygen and first carbon. Okay, from first and second, whatever double bond is there, that is shifted onto the ortho position. So your first canonical form would be what? Benzene, right? This double,
Yes.
this double bond as it is, that we need not to change. What happened exactly? Oxygen and first carbon would form your double bond, right? OH. And as lone pair on the oxygen is being utilized to form a double bond, it become electropositive. Clear? Right? And
Yes,
your
ma'am.
first carbon and second carbon negative, like that double bond has been shifted onto the ortho position to form a negative charge. Clear?
Yes, ma'am.
The first structure. Now, this negative charge has been shifted into your second carbon and third carbon. And the bond between fourth and fifth would be again delocalized at the para position. Clear? Now,
Yes.
form double bond over here. Your first carbon bond would be here. This bond would not be affected at all. It's as it is. Negative charge would become at the para position. And here double bond O H with the positive charge. Clear?
Yes, ma'am, I'm getting it.
Now again, what happened? This negative charge would be formed a bond in between what your this one fourth and fifth carbon, and bond between fifth and sixth would be shifted at the ortho position back. Clear? You'll get
Yes.
this bond as it is. The newly formed double bond would be here, right? Delocalized negative charge would be brought onto the ortho position. Here would be the double bond O H with positive charge. Okay. Now, this negative charge would be formed double bond over here, and this double bond would be goes onto the oxygen to get you phenol structure back.
Okay.
Here double, single, double, and here it will be OH. So suppose this is your first structure and this is your last structure, or I consider it as the second structure of phenol, right? So what is the difference in between this and this? Both are same, both are phenol. Only the position of alternate double bond has been changed. This is also
Yeah, yes.
bond. This is also alternate double bond. What you come to know? Only delocalized double bond has been delocalized. Correct?
Yes, ma'am.
So we cannot predict where the double bond is present exactly in this resonating structure. These all are what? Canonical form. Right? Canonical forms of phenol structure. And if I have to write the hybrid, how I will show it? This would
All of
be
them we have dotted.
your benzene ring. Inner double bond has been shown by what? Dotted circle.
Ah, right. Yes, ma'am.
You can't consider where it exactly present, right? We cannot means like confirm it where it exactly present. So that you have to show with a dotted circle. Okay, and here you have to write your OH group. So this is your
We had the
resonance.
same resonance hybrid structure in 10th grade cover test book also.
Yes, resonance hybrid bond phenol. Correct?
Yes, ma'am.
Understood? Any query about it? Just one, do you have any query about it?
No, ma'am.
Fine. The next one would be what? For the nitrate group. Shall I erase it?
Okay, ma'am.
For the nitrate group would be what now? Same way. Double, single, double, right? It will be what? Nitrogen, double bond of oxygen, and here also oxygen, correct? So what happened? This bond would be shifted over here, and here would be the delocalization of nitrogen oxygen double bond, and hence negative charge will be generated onto oxygen. The first canonical form would be in this manner. This would be double bond. This is double bond. It does not affect. This double bond has been shifted into nitrogen and carbon and nitrogen, right? Yes. Here would be oxygen. Valency of nitrogen is nothing but 3. Now we become here 4, correct? And hence we have to make it positive. Oxygen with a negative charge. Goes on Y. What you will get over here? Positive charge. Fine. Because nitrogen oxygen double bond has been broke, and that has been shifted towards the oxygen. Negative charge has been delocalized. Right? If you don't want to show that, that too fine. Positive charge would be goes over here. Because this double bond, first carbon and second carbon's double bond has been shifted in between carbon and nitrogen, and hence positive charge will be generated here. Clear? Yes? Hello?
Yes, ma'am.
Now, to satisfy this positive charge, this double bond has been shifted in between your second and third carbon, right? So you will get another structure in this way. Double bond, single bond, your double bond, and here single bond, right? Double bond nitrogen, here it will be oxygen with negative charge, and here is just oxygen, fine. But then now what happened in between your fourth and fifth carbon double bond has been shifted in between third and fourth. So at the fifth position, there would be your positive charge generated. Yeah. To neutralize it, what happened? Fifth and sixth carbon has a double bond that has been shifted in between your fifth and sixth carbon. Correct? Sorry, fourth and fifth carbon. So you will get the another canonical form in this way. This double bond as it is. Clear? Then this
Yes, ma'am.
double bond, so this positive charge would be neutralized. Positive charge would be generated at the ortho position again. Here would be the nitrogen. Okay, it would be the oxygen, and here is the oxygen with negative charge. Clear? Now,
Yes, ma'am.
similarly, to balance it, what happened? This negative charge has been goes back to the nitrogen, and this double bond has been neutralized this positive charge. Yeah, you will get your nitrate group back as it was earlier. Double
Again, the
bond.
positions will be
Yes.
different.
You can take the nitrogen. Here it will be the double bond O, right? And here it is the oxygen. What you come to know over here by looking at this your first structure and your second structure, position
They are
alternate has been totally
different
changed.
double bond
Same,
positions.
is same, your reagent is same, there won't be any sort of difference. But then we cannot predict where exactly that double bond is delocalized or where it is present. And hence you have to use it what? Resonance hybrid. So in what sense you're going to use it? Again, you
Again,
have
a dotted circle.
circle inside the ring. Okay, and here it will be the nitrate group, NO2. Correct? You may write it in a structural form, you can write it in a molecular form. That doesn't matter.
Okay.
Clear? Any query? Anything is there in your mind about it? Please let me know.
No doubt, ma'am.
Now see the next one. The important point which I actually wanted to explain, that is a dipole moment. Yeah. Yeah, polarity among the bond. Now, what is a non-polar and polar bond? Already I have explained it. I don't want to explain much. I'll just give you an overview about it. Okay. So, non-polar molecule means what? The homoatomic molecule in short. You know that the molecular are of two types, that is homoatomic and heteroatomic. Clear? Yes, homoatomic means made up of the same molecule. Sorry, same atom. For example, hydrogen, hydrogen, chlorine, chlorine, correct? Yes or no?
Yeah.
Both the atoms in the homoatomic are identical. And hence the stretching of electrons, they equally share the electrons, and that shared electron are equally distributed towards the both the atoms, right? Due to the equal strength or equal electronegativity of both the atoms, right? And hence these are the non-polar molecule. How it will be? Non-polar molecules. Now polar molecule means what? For example, HCl, right? In this case also bond is formed, covalent bond is formed by the sharing of pair of electron, correct? Yes or no? Yes. So hydrogen also shared the electron, share one electron. Chlorine also would share one electron. But then what happened? Chlorine has a more electronegativity, right? Chlorine has what? More electronegativity, and hence the shared pair of electron is shifted little towards what? Chlorine. And hence chlorine has a negative delta charge and hydrogen has a positive delta charge. And hence it become polar, right? It develop a charge and it become polar. And such a molecule are a polar molecules, which are heteroatomic molecules. Clear? Understand? HCl is what? Heteroatomic molecule. Keep it in your mind. Understanding or not? Yes?
Yes,
Yeah,
ma'am.
yeah.
Now, the next thing which I wanted to explain you about. Uses of this, means application of this polarity. Why we should learn this. What is the use of this that we are going to check. Dipole moment means what? This polarity is measured with the help of dipole moment. So what is that dipole moment? Dipole moment is been expressed in terms of the band, and it's a vector quantity. See, due to the polarity, polar molecules are also known as a dipole molecules. Yeah, dipole molecules. Fine. So these dipole molecules possesses the dipole moment. So dipole moment is defined as the product of magnitude of positive or negative charge and the distance between the charges, right? Suppose here HCl you are considering, it has a plus delta charge, it has a minus delta charge. So magnitude of plus and minus delta charge on the hydrogen and fluorine atom and the distance between them that you need to consider to calculate the dipole moment, and it is denoted by this letter mu. With the mu, dipole moment is denoted by what? Mu. It is equal to charge into distance of separation between charges. Distance of charges, right? And charge has been denoted by what? Q, right? And distance has been denoted by D. So mu is equal to Q into D. This would be the formula for the calculation of dipole moment. As I told you earlier, dipole moment is a vector quantity. It has been shown with the arrow starting with the positive. Tail would be towards the positive end and head would be towards the negative end. For example, for HF, they have shown tail on the hydrogen and head is towards the fluorine. Same manner for the HCl, if I have to write, how I'm going to write in this way. Fine. If I have to write for the CO, carbon monoxide, I'll write in this way. Understanding? Tail would be towards positive end and here at the another way, sorry, your head would be towards negative end. Clear? Fine. Now, what are the applications? Applications of dipole moments are for determining the polarity of molecule. We can determine the polarity of molecule, whether it, how much charge is being generated and what is the dipole moment for that, how polar molecule is, more polar, non-polar, etc. Then the finding shapes of molecule, right? Because if molecule is symmetric and the stretching is same, those molecule does not have a dipole moment, right? But then if dipole moment is there, it means it has a certain shape like the angular, pyramidal, etc. So it is given. For example, molecule with a zero dipole moment will be linear or symmetrical. Those molecules which have an unsymmetrical shape will be either bent or angular. For example, NH3, they have given the dipole moment is nothing but 1.47. So as NH3 molecule possesses the dipole moment, it is not symmetrical molecule, that we come to know by knowing the dipole moment. Next, in calculating the percentage ionic character of polar ions, we can calculate the percentage ionic character, right? How much percentage ionic they are in the nature. That can be calculated by knowing the dipole moment. Fine. Now see the next one. Valence shell electron pair repulsion theory. That I'll explain. And after that, BBT we will see tomorrow. See, Sidwick and Powell. These are the two scientists, right? Sidwick and Powell in 1940 proposed a simple theory based on repulsive character of electron pairs in the valence shell of an atom. It was further developed by the Nihon and the Gillips. Okay, in 1957, means it's put forth on the in the 1940s by the Sidwick and Powell, and again we can say updated or what we can say reconsidered by the Nylon and Gillips into the 1957. So what are the main postulates of this that we are going to see? The first main postulate of this is nothing but what? The exact shape of molecule depends upon number of electron pairs. See what is being said. The exact shape of molecule depend upon the number of electron pairs bonded or non-bonded. Means only bonded electrons you does not have to consider. You have to consider non-bonded electron as well. What do you mean by non-bonded electron? Lone pairs. Okay, around the central atom. So on which basis you can calculate, determine the structure of the molecule by knowing the bonded and non-bonded electron around the central atom. Okay, so exact shape of molecule depends upon number of electron pairs bonded as well as non-bonded around the central atom. For example, if you see the NH3 molecule, this would be the structure, right? Right? But then here, your lone pairs are present on the nitrogen head, and hence this structure would become a pyramidal structure. Actually, it should be angular if you see only for the 3 hydrogens, consider, right? But then it is what? Pyramidal structure due to presence of lone pair. Means in this case, you have to consider what? Bonded as well as non-bonded electrons around the central atom, and nitrogen is a central atom in this case. Now next, the electron pairs have a tendency to repel each other since they exist around the central atom, and electron clouds are negatively charged. What has been said? Electron pairs have a tendency what? To repel each other. Why? Because all electrons have the same charge, negative, negative, and like charges repel each other. Everybody is aware about it, right? And they exist around the central atom, and electron cloud are negatively charged, right? So here would be the electrons present in between each bond, that is in the form of electron cloud, and that is of negative charge. Next, third, electron pairs try to take such a position which can minimize the repulsion between them. Understanding? For example, if we go for the carbon monoxide molecule, right? Carbon monoxide molecule I will do. So here, dioxide I'll do. Carbon, here will be the oxygen. Carbon, here will be the oxygen, right? This is carbon dioxide. Means carbon and oxygen has a double bond. Here also carbon and oxygen has a double. So this carbon and oxygen go by making the angle 180 degree, right? It can be arranged in this manner as well. Why they don't arrange themselves in between this manner? Why not 60 degree? Why not 50 degree? Because these bonded electrons also may have repulsion in between due to the similar charges, negative charge. Negative, negative can repel each other. They will be the steric hindrance, and your molecule become unstable. To gain stability, these all electrons arrange themselves, separate themselves in such a way that to minimize the repulsion between them, right? And hence, the angle in between carbon dioxide, both oxygen is nothing but 180 degree. Understand? For what reason? To minimize the repulsion. Now next, the valence shell is taken as a sphere with the electron pair placed at a maximum distance. What we have to consider? The valence shell is taken as a sphere. You have to consider the valence shell as a sphere with the electron pairs placed at a maximum distance, far as possible. Next, a multiple bond is treated as if it is single electron pair and the electron pair which constitute the bond as single pairs. Multiple bond also considered as what? It is treated as what? Single electron pair. And electron pairs which constitute the bond as a single pair. Understanding? Though there are the multiple bond, then too you have to consider it as a single electron pair bond while arranging into the structures. These things you need to keep it in your mind. These are the 5 basic postulates of VSEPR theory. It is called as valence shell electron pair repulsion theory. Clear? We are going to see VSEPR theory in detail about valence bond theory. That I'll continue with the tomorrow. Right? Though tomorrow is a Sunday, I think I have to compensate one period as well yours, right? Last week I have missed one period, isn't it?
Yes, ma'am.
At the time of Eid. So that I will compensate you by tomorrow. I'll post the message about it and that we will continue. Okay. So 2 hours period would be there tomorrow. If possible, I'll join early. And as tomorrow is Sunday, I won't feel like anybody has anything to like go somewhere or something. If you have planned, please cancel it. because the term which I'm going to explain, that is quite important. Okay,
Okay.
fine. So take care. Bye.
Thank you, ma'am.
Continue.
Have a nice day.